DiagnosTech Academy today, here in the Center of Applied Research in Jena and also online. So it's my pleasure to welcome Benedict Diederich and colleagues from OpenUC2 GmbH, and they will lead us today through hands-on workshop titled From Cube to Autonomous Microscopy. And for those who do not know, and I think you will talk about it, OpenUC2 is a spin-off from the Leibniz Institute of Photonic Technology. First, we will have a short theoretical introduction and then hands-on experience here. We will try also to capture parts of it at least with an iPad, and let's see how much you can see online. And maybe next time you can come in person to our workshop here if we have a continuation of this. So we will start with the very basics of the OpenUC2 modular optics system, and that's transforming a simple cube into a magnifying glass, a mirror, or even camera. And step by step, you will explore how to build a smartphone-based microscope and then expand it into an autonomous multicolor fluorescence system using the new innovative frame platform generated by OpenUC2. And this workshop will perfectly demonstrate how open source principles and modular design can empower scientific instrumentation and lab automation, make an advanced microscopy more accessible and adaptable to everyone. So thank you, Benedict, and thank you for being here. And without further saying, I will hand over to you, please.
Thank you so much. Cool. Okay, so I think it will be very informal. So I mean, if you don't mind coming one step further, that's will be interactive after the talk, so you can also stay there for now. But thanks for giving us the opportunity to present our latest stuff. I would say we had already a little warm-up release party of the frame, but I'd say it's not quite done yet. So all the feedback you have today, it's very valuable for us to integrate that in the future. We're still iterating to have it hopefully published by the end of this year, beginning of next year. And so after this little talk, I will, or we will guide you through the steps between like how do you go from simple cubes here, from the different boxes we have for mostly teaching. So I'll tell you why we have these cubes, to eventually make bigger cubes, and then eventually learn how you integrate these cubes into this fully autonomous microscope. And for this, I will share my slides. And it will be interactive. I think for those who have listened to my talks, you know what to expect. So, right. Okay, so we have already heard that there's this little thing about open source. So you may ask, okay, why open source? And I think my favorite question is always like to the audience, so where do you experience open source in your daily life? Just like think about it for a second, and where do you think it's valuable for you? Where you take out your phone and it's like, oh, open source. Audience? No? Okay, I mean, I have an Android phone, so theoretically, like the Android system itself is somewhat open source-ish. I think it's becoming more and more closed. Wikipedia is like even like a crowdsourced. So there's plenty of different things all around us that have significant contribution from the open source community. That means there's a huge portion of people actively developing tools or resources. And I liked it a lot. And together with this fact here, actually, I've read this phrase a lot when I did my bachelor thesis, which was mostly about holographic optical tweezers, where I was developing such thing, and many people before me did that already. I'm not so much of a coder person. And then you read this nice paper, they've done all the heavy lifting, and then in the end, you want to use their code, and then you see like, yeah, you can only get the code if you have reasonable requests, whatever that means. And I think this was, at least for my PhD at the Leibniz Institute, the motivation to change that. And then, I mean, this is academic, and this is industry. So I think 3D printing, that's a big part of our setups here. That's also now open source, something that is really valuable, because 3D printers that I think many people use nowadays, they were slowly growing-ish, because there was like a big patent from one big company called Stratasys that was taken away in 2012.
And then you see that, well, this figure basically ends here.
Excuse me. The slides are in the Referentenansicht in the Zoom conference. Maybe you can change.
Okay. Okay, be with me. I think I'll just stop sharing. That's better. Good. And I think I mean, since many labs nowadays, many companies have printers and also people at home, I think this is more of an exponential growth. And then I think maybe now it's saturating quite a lot. But there were people in UK that built this RepRap. So it's a machine that is replicating itself. And then this was basically the contribution why so many different algorithms, technologies, components became so much more cheap because they became available and accessible and affordable. And there's also this 3A, what we're trying to aim for. Because like if you're in optics, and I think if you go around this institute, many other institutes in Jena, because well, Jena is the optics valley, optics is all around us with Zeiss and optic, and it's quite well, complex and also somewhat exclusive because it is not available, affordable, or accessible because it's actually quite complicated and also only very few companies are building that. And so involving the community by default is pretty difficult because you don't have access to these tools. And also making the tools understandable if you don't have them, it's actually quite difficult because sometimes you need to experience them. So, and this is basically the main motivation why we have created this modular system. And then the last bit is like, why should we care about standardization? And there's yet another comic that I like a lot, where you have all these different standards, and then there's one person coming, oh, I want to unify everything. And then they come up with the 15th standard. And that's not what we try to do. We try to implement different standards and then use those so that if you, for example, have an objective lens, that's the perfect example. There is like this Royal Microscopy Society standard. So we don't create a new thread or something. We just implement that and make it compatible with each other. Okay, other people have done it. And especially in the electronics, I think aside from the 3D printing community, many people maybe know this Arduino. It's an open source microcontroller, which just was bought by a very big company the week before last week. So open source actually does matter. And so what they did is basically something that took me quite a long time when I was in electrical engineering or during my apprenticeship. Like this thing, what you see here, it's a little LED that starts blinking. And typically for electronics, that means you have to use all kinds of capacitors, resistors, LEDs, whatsoever. And here you just plug that into your computer and the LED blinks. Not only that, because it's programmable, or like you can add different programs. That means you can also use it for home automation, robotics, microscopy. And this is then again driven by the open source community. And I think you get the point. I like open source. And this is basically just adapted to optics. So in microscopy in particular, you have like an optical system. In that case, it's a microscope, but you can also have different optical systems where you have a light source, lenses, objective lenses, and a camera eventually. And luckily, physics give us already modularization by default because of the Fourier principle, where you have different elements following one another with their focal lengths. And so we basically just drew boxes around it, called it OpenUC2, and that's it. It's open source, so you can download the design files and also modify them. And what our aim was is basically making different optics from different vendors mutually compatible to each other. And so this is then the ecosystem that is available. So there's a library where you can then actually download the parts or develop new ones and then feed that back and then make all kinds of different systems. Like, for example, this machine here on the table. And there was a journey. So we didn't start with the cubes in the first place, also not 3D printing. But then we ended up with 3D printing. And eventually now, since we have so many cubes out there, there's already the inject molding in place. So because you need at one level more precision, also more reproducibility. And since you need a lot of these cubes, we have decided to injection mold them locally. And with this, over the last few years, we have been part of many different initiatives worldwide where we taught how to use optics or how can you use optics for your protocol. So there are also some nice stories where people here in, I think, Ghana use them somewhere close to the desert in a context I've never experienced. So it's even in French. So they taught how to design optics with our systems, which was quite nice.
Other people have used that, for example, to challenge students. So there's a recent study from people from Eindhoven where they have used our cubes to let students build, for example, a light chain microscope, basically from scratch. And so this was the foundation for our community worldwide again. So, but this is only the cube thing. So you will experience how to use these cubes once you get your fingers dirty, let's say. And for this, there's also an open source documentation in which I will go into a little later. But you may ask yourself, okay, there's this cube, it's very nice. It's maybe nice for kids. You have, for example, a little magnifying glass, and you can use that for maybe a little smartphone microscope. But how could I use that for research? And very often you have this situation, I think also here in this building, where maybe the PI is a bit frugal. He or she doesn't want to spend so much money on buying a new microscope. Also, you have the problem, like if you have a PhD student and the person's leaving, all the knowledge is lost. So if you build a microscope on the optical table, who is actually maintaining that once the person is finished? So there are different people with different interests, and there is this thing that eventually you need to have a system that is somewhat standardized, like our cubes, but is also professional. And so the philosophy for OpenUC2 now is basically the center of this whole thing is the cube, and the function that is basically defining what the cube can do is inside. So it can open the cube and, for example, add the lens or a focusing element, or maybe an XYZ stage, or also some electrical devices that illuminate your sample. And then with these modules that define the function, you can then build setups, because multiple of these different elements form a function. And then once you have, for example, different functions and maybe these setups, then you can also create, well, we call them boxes or collections, which are then, for example, ready for schools, but not necessarily, can also be for industrial use. And then once you have all the way down understood how this whole thing works, because you can actually start in elementary school and then go down to the research institute or industry, then you can apply your knowledge to this thing. And it's always the same footprint. So what you will see later here, you can basically move out this whole mechanism, and it's still filled with cubes. I show you that in a second. And then the question is, of course, okay, how would you then actually do that? So taking a very simple, or like at least for me, simple example. So maybe a biologist, she needs to have a microscope for observing HeLa cells maybe every minute at GFP excitation, so 488 nanometer excitation. Then you may end up Googling what's actually a fluorescent microscope. On the right-hand side, that's just an arbitrary design that I've taken from the internet somewhere. But what you need to worry about is like you have a light source that is matching your excitation spectrum from your cells. You have some filters, you have some objectives, and maybe also a detector. And then the simple step here would be, okay, for each of these elements here, you take one from our library. So for example, an LED, some lenses to form something called ocular illumination. You have your focusing element here, your cell, and your detector. And that's basically a method we just call cubification, because you translate an idea into cubes. And it's literally just that. So for each of these elements here, we have a little cube in our library. And since you can stack and orient all the different elements in all three directions, it's also very straightforward to build this system in the end. And so just some examples here. So you can use this whole thing in an incubator for fluorescence. In that case, it's autofluorescence. And since not everybody can do it, because maybe that's also some of our knowledge that we have built up over the last few years, we decided, okay, we want to open this up so that people actually have the ability to experience, okay, what components are actually available, and how can you construct that? And this is the part which is maybe also very comparable to what Arduino has done, because they created this big library of code snippets where you can just use different libraries for home automation, robotics, microscopy. And this is the equivalent for us. So each of these modules here is basically a code snippet. You can reuse it, and then you can build up all kinds of different setups. And so the setup what you see here is, again, this fluorescent microscope that you can use without this frame. So the frame is basically literally what it says, like it's a frame to hold our optics, but at the same time, we call it fast, rigid, automated microscope engine because it can move and it's fully autonomous. So you can, for example, move the stage, have access to lasers, etc. And since we want to preserve this idea of open source, there's also the ability to share the designs and then also use it. Right, and how does it look like for a frame? So I've brought some of these inner cubes, and one challenge for today, once you've learned how to build this coreBOX smartphone microscope, you can start building a very simple microscope, but it's already a little bit advanced because it has the ability to detect polarization. So and for this, we have some components here. I haven't brought all the library cards, but two very important ones, which is the polarizer and the analyzer, which is here. And then, so not sure, I think you cannot really see that. So the idea is that you polarize the light linearly, and then with an analyzer, you filter out the nonlinear component from the polarized light. And so with these two components, you can already build a cross-polarization microscope to detect, for example, birefringent in stress of plastics. And that's what we try to do, I guess, here. So, and you see the function or like the imaging modality is only dependent on the inner cube or like the cubes you are surrounding it with. So there's polarization. We also have like a little galvo scanning component that you can start in for example, film imaging. So that's called fluorescent lifetime imaging. That's in collaboration with some people from Italy. They built the lasers and the detectors. And what we also have here on the stage is the fluorescent microscope, which is not with a LED, but with a laser, and also some samples that we can show later. And so how this then actually looks like. So, so this is some data that is created from other people. So this here, for example, is single molecular localization microscopy. So you could go down to single molecular localization level. It means like you can detect few photons and go down to 50 nanometers. So that's a publication from people in Berlin. And you can do live cell imaging and also multicolor fluorescence imaging. So, and of these, so the idea is, of course, that our interest as a company is that we provide you with the tools and make money. And so this is basically a very linear approach. So you can start with the cubes in the boxes, but you can also apply the same methods just here. So if you want to start on a small field of view, you maybe don't need to have the full frame, but then you can always apply that afterwards. So, right. And if you're really keen to do that in 3D, there's also a new tool, which is very experimental right now, but you can configure this thing all in the browser in 3D, of course. Other things that we're working on, but I figured out that at least this part is missing on the table today. We have some autonomous or like automatic calibration routines because people are asking, okay, you have this microscope, it's cheap, but is it also like a valid research tool? That's a very valid question. And for this, you need to have calibration tools to actually be quantitative. And there are some software pieces inside this box here. I think most of the stuff is still kind of experimental, but we're converging to something that's production ready. But the microscope is optimizing itself so that you have, for example, automatic point spread calibration, and the stage is calibrating itself. And we thought it would be fun to make that a game. So the sample features a little maze, and then you can basically, alongside with the sample, solve the maze, and then in the midterm future also, well, calibrate how well the stage is actually linearly moving in all directions. Thing about the film, just to convince you that you can do other things than just like the basic modalities than fluorescence. This is giving you the spectrum of like, or the lifetime of your fluorophore. So how long does it take to turn it off or like itself? And then since I mentioned we are open, people from Italy, the Film Labs people, they just use our toolbox for building the imaging with the galvo scanner, and then you can integrate that as a single cube inside to make it compatible with an ordinary microscope. Right. The last bit, and then we can directly go into the demo mode. I think there's a trend going on about lab automation, and there's also something where we try to apply it. It's not production ready yet, but there's also a very nice benefit of open source software. So we see ourselves, or like see the microscope itself as a little robot. So you have, for example, pipetting robots. In our case, that's an Opentrons. There's a little robot arm that is eventually moving slides back and forth. And then the microscope itself is just a sensor where you give or provided with samples, play start, and then you autonomously scan it, and then eventually tell the pipetting robot, okay, you have to wash your samples a little more because the antibody staining is not quite right yet. And so this is part of a bigger workflow, and the microscope is just one service. And we're teaming up with some people from Architect, where this is basically the binding glue between different components like image processing, robots, and everything runs, well, very much distributed. So the microscope can stand here, can be in Berlin. And so the consortium that we've created is actually exactly like that. So the microscope is here, the robot arm as well, also the pipetting robot. The image processing is at the Helmholtz Institute in Berlin, and the people who provide us with the protocols are in Helsinki. And so this glue from Architect makes it possible to talk to different components with the same language at different locations, essentially. So this is how it looks like. We have this Opentrons, which is a pipetting robot. You have a frame microscope. You have a little Ferrino robot arm, some image processing. They all run through this signal processing. And then with this, you can create this workflow where there's eventually a robot arm picking up the sample, bringing that to the microscope. The microscope is doing imaging, and then the algorithm is deciding whether we should do some further staining or not. And with this, I'm already at the end of the presentation. Well, I shouldn't put myself first, should start with this one here. Of course, this is only possible with our team. Some of them are here. So we have a great team at the Beutenberg here at the tip. And we are constantly growing and trying to find our way through what's actually our niche market. So I think this is something that we are just trying to find out. I think now it's settling more and more. And so we have Christian, Armin, Jens, and Christine, mostly for the product itself. Then we also have new software people. And then like Ethan, I've seen, Florian's not here. Stefan's also not here. And then, of course, Harwan is also here. And then Sebastian. And together we are trying to basically shape how open microscopy can look like. And with this, I would like to end because it's like already half an hour. And so the agenda for today is having fun. That's the first place. So we have two boxes here. Maybe we can put them here. Then you don't need that hard. And the boxes, they come with an open source OpenUC2, which I must admit it's not perfect yet. There's also a little bit of story behind it. So the boxes are the first product that is scaled by means of above 100. And so we're collaborating with some people from workshop for people with disabilities. And they actually have very much fun to assemble these devices, which is also a very nice thing for us to see that, well, not appreciated only during the experimentation, but also during the assembly. And if you go or follow this link of the QR code that is on there, you will probably go here.